Hello everybody, and welcome to lecture 25 on power series. So we're going to start with a definition of what a power series is. So a power series is a series of the form, and it's n equals 0 to infinity, of c sub n times x to the n. So if you maybe fill out the first few terms here, if I plug in n equals 0, I would get c of 0 plus, and if I were to plug in 1 for n, I would get c sub 1 x to the first power. If I do one more, if I plug in n equals 2, I'd get c sub 2 x squared plus. And it just goes on forever like that. So x is some variable, and then the c sub n's right here, these are called the coefficients of the series. So these c sub n's right here are called coefficients, and they are just constants that are in front of the variable x. And then a more general way to write a power series is like this, where you have the coefficient c sub n and then some variable x minus a fixed a. So we say that this right here, let me write out the first few terms first. So if I plug in n equals 0, this piece will go to 1. So this is c sub 0 plus, if I plug in 1, I get c sub 1 x minus a to the first, plus c sub 2 x minus a to the second, and this continues forever. So this right here is a power series, and we say it's centered at a. So a is some fixed value. And this type of series right here, this will always converge when x equals a. So when x equals a, this portion would be 0. So all of the terms that I would be summing here, this one right here would be 0. This would be 0. So I'm just left with c sub 0 plus 0. So by convention, we're just going to assume that these power series will always converge at their center at a. So power series, they converge or diverge, but it depends on the value of x. So a power series can converge for some values of x, but not others, or it could converge for all values of x or none of them. You're going to see all three cases in this video, so I'm going to get you comfortable with that. So let's start with this very first example right here so we can practice. So it says, for what values of x does this series converge? So we have to rely on series tests from previous lectures. And for a lot of these, a good way to go is the ratio test, because you see factorials or you see powers of n. So what I'm going to do is I'm going to do the ratio test. So this isn't super new stuff. We're still going to use the ratio test. So what I need to do is I have L as the limit as n goes to infinity of the absolute value. And then I have a sub n plus 1. So that's when I plug in n plus 1 for n here. So a sub n plus 1 is n plus 1 factorial x to the n plus 1. And then over a sub n, so this is going to be n factorial x to the n. So in here, what I plugged in is our a sub n plus 1 over a sub n. So this is just the ratio test. OK, so now from here, what I notice is n is a positive number, and if I or 0. So if I plug in these values for n, this will always be positive. So I don't need absolute value bars around the n plus 1 factorial or the n. I know that's always going to be a positive value. So I'm going to rewrite this as the limit as n goes to infinity. This will be n plus 1 times n factorial over n factorial. So remember, from our previous lecture, n plus 1 factorial can be broken up into n plus 1, and then you have n factorial afterwards. And then what's remaining in here? Well, x to the n plus 1 divided by x to the n, all those x's cancel out except for one x in the numerator. So I have x that's still left in here. And I'm not sure if the variable x is positive or negative. I know because n is 0 or 1, 2, 3, I know these are all going to be positive, so they can come outside the absolute value bars. But we're focusing on this now. So these n factorials also cancel, and I get the limit as n goes to infinity of n plus 1 absolute value of x. And now, for the ratio test, when does this converge? So you always have to ask your question, when is L going to be less than 1? And really, I should say, for what x values is that going to be true? Well, n is going to go to infinity, right? So n plus 1 is going to go to infinity as n gets large. So really, this will go to infinity, except for one very specific case, and we talked about it over here. So when x is equal to its center, then the series will automatically converge. Well, if I write this in that form, because the form is x minus a, right? There's nothing here, so actually the form is x minus 0, huh? So it's x minus 0. So if you plug in 0 here, this is the only exception where you will have the limit as less than 1. So I'm going to say we have this is true, except when x equals 0. So the conclusion I can make here is that this series converges when x equals 0 and diverges for all other x values. That's because otherwise, no matter what x I plug in here, this is going to go to infinity, and then suddenly I'm not less than 1 anymore. I have some positive number times infinity here. OK, so this one diverges for everything except for x equals 0. Let's take a look at this one. So this is also the ratio test. It's just a little more difficult with the arithmetic, but we're going to do it the same way. So we're going to say the limit, or sorry, capital L is the limit as n goes to infinity. I'm going to need a lot of room, so I'm going to draw a much larger one this time. In the numerator, you need a sub n plus 1. So I'm going to plug in n plus 1 into all of these spots. So I get negative 1 to the n plus 1, x to the 2n plus 1, over 2 to the 2n plus 1. And then I have n plus 1 factorial all squared. And then in your denominator, you have a sub n, which is just the standard thing I have right here. So this is negative 1 to the n, x to the 2n, over 2 to the 2n, and then n factorial squared. So we have to simplify this as much as possible. So for starters, if you're taking the absolute value of this, these factors of negative 1 completely disappear. Not only do they cancel out except for one of them here, but if you take the absolute value of this factor of negative 1, it's gone. So that's going to be gone. Let's look and see what else I can cancel in here. So you see, in the numerator and denominator here, I have these factors of x to the 2 and plus 1x to the 2. You also see these powers of 2. So a lot is going to cancel out here. Let's go ahead and flip. We're going to keep change flip. So I'm going to keep the very first fraction and just get rid of these negative 1s because they're gone since we have the absolute value. So I have x. Let's distribute this. I have 2n times x squared. I'm going to separate those. And this is divided by 2 to the, here I have 2n, times, and then I get another 2 to the 2. And then this right here, I have n plus 1 factorial squared. That's going to be n plus 1 factorial times n plus 1 factorial times. Now I'm going to flip the denominator. So if I flip that, I get x to the 2n in the denominator. And in the numerator, if I flip this, I get 2 to the 2n. And then here I get n factorial times n factorial. So that's me flipping everything, separating it. Now you're going to see a lot of cancellation. So here these 2 to the 2n's cancel. I have x to the 2n also cancels. N factorial over n plus 1 factorial, they're all going to cancel except for the n plus 1 on the bottom. And there's 2 of those. So in the denominator, I'm just going to get n plus 1 squared. And that's because, again, n plus 1 factorial is n plus 1 times n factorial. So each of those are equal to this. I also have a 4 still sitting in this denominator. Anything remaining in the numerator, well, these have canceled out with these now. And the only thing I see is x squared. So a lot has reduced. We're left with this. Notice x squared is a positive number for any x. N plus 1 is going to be squared, is going to be positive for any n. So I don't need absolute value bars anymore. 4 is positive. Everything is positive, so I don't need absolute value bars. And then no matter what x value you give me, what happens to this limit as n goes to infinity? Well, the denominator gets huge. So I'm always going to have some number divided by something that goes to infinity. This goes to 0 for all real numbers x. Doesn't matter what x you give me. So this time, it's another extreme case. For this one, you only had x equals 0 as the answer. For this one, for every single x you give me, this is going to be true. I'm going to have this be less than 1. So this means the series converges for all real numbers x. So these are 2 of the 3 cases that can happen when you do these problems. You can get that it only converges for the center. This time the center is x equals 0. I showed you that. Or you can have that it converges for everything. And in the next part of this video, we're going to explore the the last case that could happen. So there's a third case to this. I'll see you in just a second for that. Welcome back to part 2 of this video. So now I'm going to cover an important theorem that talks about those 3 cases of convergence, where I've already talked about the first 2 in the previous part of this video. So for a given power series written here, there are only 3 possibilities that could happen with regard to its convergence. So the first case here is that the series, I don't know why it said then, this series only converges when x is equal to the center A. So this is case 1. We saw that with the very first example I did in this lecture. Case 2 is the series converges for every single x, and we saw that for example 2 in this video. Now the third one that we're about to talk about is the more interesting case. So there will be some positive number, capital R, such that the series converges for all x, absolute value of x minus a is less than r, and the series will diverge for all values of x where absolute value of x minus a is greater than r. And we call this capital R something special. It's called the radius of convergence. So another way of writing this, if you have this absolute value here, is I could say that x minus a is strictly between negative r and r. Another way you can think about the absolute value is it's the distance between x and a. So as long as that distance is within some capital R, we have convergence. Otherwise, if the distance is greater between those 2 than r, then you have divergence. So you're going to see how we calculate this r in just a second here. So let's start with this example. It will start just like all the other problems. We're going to do the ratio test to figure out when this converges here. So let's go ahead and do that. So we have the limit as n goes to infinity. If this right here is my a sub n, then a sub n plus 1 is going to be n plus 1 times x plus 2 raised to the n plus 1 divided by 3 to the n plus 2, because I'm going to add 1 here. So that's my a sub n plus 1. And now I'm going to rewrite a sub n. So this is just n x plus 2 to the n divided by 3 n plus 1, raised to the n plus 1. So our goal is going to be to simplify this. So this is the limit as n goes to infinity. Now what do we have here? So I could keep change flip. I guess I will. So what I'm going to have now is if I keep change flip, I'll do giant absolute value bars. Keep the first fraction, which is n plus 1, x plus 2 to the n plus 1, divided by 3. I'm going to split this up. It's going to be 3n plus 1 times 3 to the first power, times, I'm going to flip the other fraction here. So this is going to be 3 to the n plus 1, divided by n x plus 2 to the n. And now we do lots of cancellation. So the limit as n goes to infinity of, here I have x plus 2 to the n plus 1, and here I have x plus 2 to the n. So all of them cancel, except for just one of the x plus 2's on top. So I have n plus 1 times x plus 2. Here I have 3 to the n plus 1. It identically matches with this one, and there's a 3 still remaining in the denominator. I'm missing this n right here, right? That's the only other thing. So now I have the limit as n goes to infinity of this. And what I'm going to ask myself now is, are there pieces of this that I for sure know are positive? And yes, I do. N is 0, 1, 2, 3, etc. N is going to infinity. So what I'm going to do is I'm going to bring out the n plus 1 over 3n. Because I'm very certain that because n are positive numbers, n plus 1 and 3n are positive. So I can just bring that factor out of the absolute value. And I'm left with just x plus 2 in the absolute value. And now as we take the limit as n goes to infinity, this is the ratio of the leading coefficients. This is going to be 1 over 3. And now convergence only happens for the ratio test if you have that this limit is less than 1. So what does it mean for a limit, this right here, to be less than 1? Well, I can multiply both sides by a positive 3. And remember, but because I do that, a positive number doesn't flip the inequality. And now if you have some value here, an absolute value that is less than 3, then you can turn this into a compound inequality. You can say this is the same thing as negative 3 is less than x plus 2 is less than 3. So that's true. And then if I simultaneously solve this by subtracting 2 to each piece of this, I'll get minus 5 is less than x is less than 1. So for all of these values of x, we have that the original series converges because it satisfies that the limit is less than 1, which is the criteria for the test, one of the criteria for the test. So let's write that down. We have the center of my series. So look at what the series was. It was this. X minus a to the n is the form of the series. What number is a this time? A is negative 2, right? You plug in negative 2, and you get plus 2. So this time, my center is at negative 2. And then I know all the way up until 1, we have convergence. And then on the other side, the opposite side, I have negative 5. And I have convergence here as well. So I would say my radius of convergence is half of the length of this. And notice negative 2 is right in the center. That's always going to be true for these, if you've done it right. So the center is always going to be in the middle of these two numbers. What's the radius? Well, the distance from here to here, or on the other side, is 3. So capital R, my radius of convergence, is 3. And I would say, just giving you some more lingo here, the interval of convergence, we're going to come back to this, but I know it does include all the numbers between negative 5 and 1. The problem now is I don't know whether to put brackets or parentheses. I don't know whether to include these numbers. So just in this third case that we're doing here from the theorem, you have to test the two endpoints because it could be convergent for one endpoint and divergent, or both convergent. It could be anything. So you have to test these. So how do you test them? Well, you take each number in question, plug it in for x in the original series, and use a previous series test to get an idea. So let's go back to the original series and plug in -5 for x. So if you do that, you get summation n equals 0 to infinity, and -5 here would give me -3 to the n, divided by 3 to the n plus 1. Let's try to simplify this. So here I have n equals 0 to infinity. I'm going to break up the numerator into -1 to the n times 3 to the n. That's how I'm breaking up -3 to the n. This can be broken up into 3 to the n times 3 by splitting that power. And then if I go ahead and cross these out, I have that I'm left with n equals 0 to infinity, n over 3 times -1 to the n. So here, I could use a very straightforward test to show this diverges. By the test for divergence, if this is my a sub n, the limit as n goes to infinity of a sub n, it's not equal to 0, right? Here I have n over 3. That limit's going to go to infinity, and then this is just going to oscillate back and forth between negative and positive giant numbers, basically. This doesn't go to 0, so this means that we diverge here. And the reason I gave is by the test for divergence. Take the a sub n to infinity, diverges. Very similarly, you can check this one, and I think it works out to be the same thing, but let's just check it to make sure. So you want to plug in 1 this time into the original series. So this gives us n 3 to the n over 3n plus 1. But you're going to see this reduces to something similar. So I have 1 extra 3, factor of 3 in the denominator, so this is n over 3. But again, if this is my a sub n, test for divergence, I could show the limit as n goes to infinity of a sub n. This one is infinity, which is not equal to 0. So again, we have divergence. So now if I take a look down here at my final interval of convergence, based on the two things I plugged in and what shook out there, you don't include either of these in the interval of convergence. So this open interval is my interval of convergence. And in this case 3, you have to check both of them because it could be different every time. So it just so happens that both of them diverged here, but you need to check both cases. So definitely, let's just drop my paper. Definitely, case 3 is the most involved, for sure. OK, let's go ahead and look at this last problem. So it says, suppose you have some power series here. So here it is. We know it converges for x equal to -4. And it diverges for x equal to 6. And then it says, what can you say about the convergence of the following 4 things? So for a problem like this, I immediately draw a picture. It helps me immensely. You need the center. So it's not written here, but remember, the form is x minus a. So if they didn't give you an x with something, the a had to be 0. So recall over here, it was -2 because they gave us x plus 2. But if there's nothing here, you can assume it's 0. So this is my center. Everything is based right here at the center. At -4, I have some information. I know we're convergent at -4. So the way this works is case 3 of the theorem tells you you're convergent for everything all the way up to that -4. The distance within that those 4 spaces, you're always convergent for all those less than some capital R. So everything from 0 to -4, we know it's convergent. Another important thing you really need to know is that we're talking about distance. So from the center, you're also convergent for a distance of 4 on the other side. So it's symmetric. So because they tell you -4, x equals -4 is a convergent series, you get that like the symmetric case. Everything up to 4 distance here is convergent, except we don't know the endpoint. The distance is 4, but you would have to test 4 separately. So we don't know that this one converges. But we do know -4 converges because it tells us it converges at -4. So I'm going to fill this in. This is open. It's a question mark. I don't know whether it converges or diverges. And then it says it diverges for 6. So we'll jump up to 6. And it says at 6 it diverges. So right here, and anything that's a greater distance away from the center, these all diverge. So 7, 8, 9, they would all diverge. That same distance reflected on the other side, if you're 6 away from the center this time, so over here, 6 away from 0, you also diverge. So anything 6 distance and greater, so -7, -8, those would all diverge. And just like before, we don't know exactly what happens at -6. You'd have to test that endpoint. But I don't know that diverges, but I know everything of 6 distance and greater from 0 diverges. So you've got the symmetry going on. If it wasn't centered at 0, I think you'd really want a picture, right, of what's going on, just so you can keep track of everything. OK, now that I've drawn a picture, let's look at this series. So we have the series of C sub n. The question you need to ask yourself is, what is x? Like, what did they plug in for x? They're going to take this series and plug in an x value. So if x disappeared, what number did x have to be? It's 1, right? If you plug in 1, you get 1 to the n would be n. So here x is 1. And then you need to compare over here, but 1 is in this convergent interval. So here we have that we have a convergent series, because it's within 4 spaces of the center. Let's take a look at this one. So compare this to the series. What did they plug in for x? You'll see C sub n, you have -3 to the n instead of x to the n. So here, very clearly, they put -3 for x. Let's look at our picture. -3 is in the middle of this convergent piece right here, from 0 to -4. This is also convergent, because it's only 3 spaces away from the center, right? And we're good up to 4 spaces at least. This one right here, I'm going to convert it a little bit. So this is the summation, n equals 0 to infinity. -1 to the n times 9 to the n, that's -9 to the n. And now you can really clearly see what it is, right? Here's C sub n. And they had to plug in -9 for x. So this time, x is -9. This is much more extreme than this -6. It's 9 units away from the center. This has to diverge, because it's more extreme than the 6 away that diverged. So this one diverges. And then here you can see they plugged in 5, like definitely. Here's C sub n. So 5 matches with x. 5 is interesting because it's like no man's land. It's like we know stuff up to 4. We know stuff after 6. Anything could have happened here. We really just don't know what's going on in this area. So we just say we don't know. Or you could say not enough information, because there's this gap where really anything could happen. So, all right, I hope that helped you visualize those. If I had more time, I would love to do even more examples. I think it's important for this section especially. So go find more examples of power series and use the ratio test to practice when these converge. And when you're done, identify which case it was. Was it this, this, and this, or this? It should be one of these every single time. All right, until next time, I'll see you in lecture 26, and have a nice day. Bye.